Hello everyone, let us discuss the simple and important issue of the transfer function of the linear system. Uh, so let's start by saying that the transfer function of the linear system is the topic of this lecture. Function of linear, and I will add linear time invariant system. Variant system. Functional time invariant. This is usually called LTI system because linear time invariant systems. What does it mean, LTI? It means that our state space representation given by the AX plus BU Y equal CX plus DU is given by the matrices A, which is of n by n size matrix. So this is n by n. B is a matrix n by 1 for the CISO system, single input, single output, and C is a matrix that is 1 by n is equal C. Okay, and transfer function of the system, we will assume initial conditions equal 0, is given as follows. We apply Laplace transform, we obtain x of s minus x0 equal a of x of s plus p of u of s, and this finally leads to the y of s when we apply 0 initial condition, and we obtain si minus a minus 1 b u of s. Okay. In other words, this expression is going to be some transfer function g of s that relates input here and output by g of s. In other words, we have the notion that u of s multiplies this black box for us, which is the transfer function g of s, and provides the y of s. Okay? And one of the important characteristics of the linear system are that if we have the input into the system, which is given here as a g of s, the system will follow the input that is applied to it. So let us assume that we have an input to the system e to the alpha t, that's just arbitrary signal, and the signal looks as follows: e to the alpha t, that's arbitrary input, and this is time here, and the claim is that output of the signal is going to be same signal multiplied by the g evaluated at the characteristics of the signal. This is a very interesting notion because how we can demonstrate something like this, that this signal just passes through this linear system and it just amplified or attenuated by the gain. This is just a gain because G evaluated at alpha is just a scalar gain that multiplies the signal. But let us demonstrate this very important feature of the linear system. So if we have e to the alpha t, which multiplies u minus 1, t, which is step input, we take the Laplace transform of this expression, and we already learned that Laplace transform of this expression is going to be s minus alpha. So this is s minus alpha. Look at that. Minus alpha, such that when we combine g of s as a transfer function with the input, we get that output of the system is nothing but g of s 1s minus alpha here. Since g of s is a stable plant, infinitely stable plant, g of s can be written as n of s p of s. And we know that we can express g of s as factors s plus s1 multiplies s plus sn. So we have n factors for the p of s n-ordered polynomial, such that finally we get the n of s plus s1 s plus sn. Those are all bars that are coming as a solution of the polynomial p of z. And here we have a 1 by s minus alpha. Okay, and the question is that what is y of t now? What is the response of our system? And we say no problem, we will obtain the factors, and if we take inverse Laplace transform of y of s, we'll get to y of t. Therefore we write y of s, as a0 divided by s minus alpha plus a1 divided by s plus s1 plus a2 divided by s plus s2 and so on, plus a n s plus s n. And now we are interested in finding these coefficients. So a0 is going to be n of s plus 1, all these terms, s plus sn, s minus alpha multiplies S minus alpha. And this is just evaluated at S equal alpha, at the root of the alpha. So these two is cancelled, and we have that n at alpha and p alpha, which is nothing but g at alpha. Okay. Other coefficients will be just found in the same way as n of s divided by p of s s plus s1, and this expression evaluated at s minus s1, and so on. So if we repeat this for all other coefficients, in this way we will have solution for the a of n as n of s, p of s, and here is s plus s. We have to add here 1 by s minus alpha. We should not forget that expression s minus alpha as well, because this is this entire expression that always has to be written. So this is evaluated at s minus s n hat. Okay. So finally, we obtain expression that says y of s is going to be g at alpha e. This is in s, so let us write this still in the form of the s, and then we will easily write this in the form of the time evolution. So this becomes 1 by s minus alpha plus a1 s plus s1 and plus all these other terms plus a n s plus s n s, such that we recognize that this is just g at alpha multiplies e to the alpha t plus a1 e to the minus s1 of t plus a of n e to the minus s n of t. From this expression, we observe that if plant is stable, which is the majority of the plants, these terms is going to 0. This term is going to 0. So finally, we have that our output is the output of the signal that is just amplified by the g of alpha. This is very important of the linear system, and we will explore these important properties of the linear system in the filter design and in later on studies.